On LR3-1, we'll identify the hypothesis and conclusion of statements, write conditionals, converse, and biconditional statements, draw Venn diagrams, and identify counterexamples. So we're going to use this as kind of our base point for all of these definitions as we're finding examples. So every creature who drinks water will die. Really overdramatic, but technically true. And if I write it as a conditional statement, I'm going to have if blank, then blank. The if part is the hypothesis, and the then part is the conclusion. So if I go back to that example, every creature who drinks water will die, I could write that as if a creature drinks water, then it will die. Notice the hypothesis is a creature drinks water. The conclusion, it will die. My counterexample is going to be anything that proves that a statement is false. And I only need one. So if I have one creature that never ever drinks water, or that drinks water but never dies, that's my counterexample. So if I say all math teachers work at MMW, all I need is one math teacher who doesn't work at MMW to prove that statement is false. If I say all girls have long hair, all I need is one girl to have short hair to prove that statement is false. Okay, so you don't need a bunch of them, you only need one. My converse then is going to swap my hypothesis and conclusion. So the if and the then stay there. But if I have if A, then B, I'm going to write that as if B, then A. So going back to every creature that drinks water will die, I would say if a creature dies, then it drank water. And it's really important to realize that just because a conditional statement is true does not mean the converse is. It is true that every single creature that drinks water will eventually die, but it is not true that every creature that dies has drank water in its life. A creature could have been born, never ever drank water, and died of dehydration, okay? Just because the conditional is true does not mean the converse is. If I have a situation, though, where both the conditional and converse are true, I can write it as a biconditional, and I get A if and only B, or I could have B if and only if A. And that B should be there. I don't know what I was doing. So I could write a creature dies if and only if it drank water. Or I could write a creature drank water if and only if it dies. Okay, they're the same idea. So Venn diagrams are something that you've probably seen in language arts or maybe even social studies, but they're really actually a mathematical thing, and they were invented by John Venn, this guy. And he was a mathematician who was really into logic, and he used circles to show where things relate. And you're used to seeing them look like this. But I could also have a Venn diagram where one set is completely within the other, and I could have two completely separate sets where neither overlap whatsoever. So we're going to practice this a little bit. I have the statement, if you finish your dinner, you finish dinner is the hypothesis. Then you can have dessert. And if I flip those ideas, it becomes if you have dessert, then you finished dinner. For my Venn diagram, I've got all the times I've ever had dinner. I'm going to have all the times I ever got dessert. And notice there's some situations where I didn't finish dinner, but I still got dessert. So I'm going to look for a bicondition or a counterexample rather than a biconditional. And my counterexample could be, parents are pushovers and they gave in. Or it could be something like grandma is babysitting and she always gives you a cookie anyways. Or maybe it's your birthday and okay, you didn't finish your peas, but you can still have a slice of cake because it's your birthday, whatever. You only need one counterexample though. We'll do another example. We have if you study for the test, then you'll do well. Your hypothesis is you study for the test. The conclusion is you do well. My converse flips those ideas. So I'll get if you did well, then you studied for the test. And in my Venn diagram, I've got all the tests I've ever taken and studied for. And I've got all the times I've done well. And notice there are times I didn't study and I still did well. So my counterexample could be something like test was easy. I didn't study, but I still did really well. Great. On this next one, we have if you have a driver's license, then you can legally drive. My hypothesis is you have a driver's license. The conclusion is you can drive. And I'm going to flip those ideas to write my converse. So if you can legally drive, then you have a driver's license. Here's all the people who can legally drive. Here's all the people who have driver's licenses. Okay, so you have to have both, which means there are no counterexamples. There's no one out there who doesn't have a driver's license who can legally drive. And there's no one out there who can legally drive who doesn't have a driver's license. So I'm going to write it as a biconditional. And I'll say, you may legally drive. If and only if you have a driver's license. I could have done the other order as well. I could have said, you have a driver's license if and only if you may legally drive. Either way works. We'll do two more examples. So we've got if a polygon is equilateral and equiangular. So my hypothesis is a polygon is equilateral and equiangular. Then it is a regular polygon. My converse would be it is a regular polygon, or if it is, then it is equilateral and equiangular. When I draw out my Venn diagram, I've got all the polygons that are equilateral and equiangular, all the polygons that are regular, and they overlap. So I'm writing a biconditional. Okay, if they're the exact same, if the converse is true and the conditional are true, I write a biconditional. So a polygon is equilateral and equiangular if and only if it is a regular polygon. Businesses also do this. So if we take Target, expect more, pay less, I can write that as a hypothesis and conclusion and then a conditional. So if you expect more, and pay less, then you shopped at Target, is what they're trying to imply. And you could make the argument that they're trying to say it the other way, that if you shop at Target, then you expect more and pay less. You really can argue either direction. So for my conditional, I'll say, if you expect more and pay less, then you shopped at Target. My converse flips those. So if you shop at Target, then you expect more and pay less. If there's any counterexample out there, so if there's ever a time where you get a better deal at anywhere other than Target, that's your counterexample, and it proves the whole thing is false. So it could be a better deal elsewhere. It could be that you shop at Target, but you don't expect more or pay less, etc., etc. Okay, you don't need a biconditional if you can come up with a counterexample.